a few interesting things about infrared spectroscopy. This is a typical example of how the infrared spectrum of an aromatic compound looks like, specifically the spectrum of toluene. And as you can see, you can find carbon-hydrogen stretches related to the aromatic ring. So these hydrogens attached to the benzene ring. You can see the carbon-hydrogen stretch from the aliphatic chain, from this methyl group, this carbon with single bonds. And we have this interesting thing here, which can be, I know they look very small, but it can be quite indicative. If there's nothing else happening in that region, it can give you an indication that you have an aromatic compound. And they are due to, they're very weak bands, and they are due to the bending mode of the carbon-hydrogen bond of these hydrogens, the ones attached to the ring. And they're typically called OOP, and OOP stands for out of plane. So out of plane bending of those hydrogens attached to the sp2 carbons. And again, they are weak, but they are very characteristic, and they appear in an area of the spectrum in which around 2000, in which typically, unless you have perhaps a nitrile group, there's nothing else going on. So they might be useful to, you know, they can be sometimes useful to identify the presence of an aromatic, a benzene ring in your structure. I've mentioned hydrogen bonding in previous videos. Hydrogen bonding influences the stiffness of the bonding between the oxygen and the hydrogen. So it will alter the frequency of vibration. The stretching modes will appear in a different, slightly, you know, they will appear displaced. And if you compare, for example, the region of the spectrum in which the OH stretching mode appears without and with hydrogen bonding, it can really shift the bond. And that when the hydrogen bond is especially strong, like for example in carboxylic acid, as I've mentioned before, it can be quite indicative, and sometimes it moves to overlap with other bands that are already there. In this case, the carbon-hydrogen bonds, stretching modes. A little bit about infrared inorganic compounds. There isn't a lot, but it can be useful sometimes, for example, to identify CO2, to identify carbonates. Simple inorganic compounds, sodium chloride, potassium bromide, etc., do not have vibrations in the infrared region used for infrared spectroscopy, which is why they can be used. Sodium chloride and potassium bromide are used as sample holders when you need to sustain the sample to put it in the infrared spectrometer. And more complex anions, sulfates, nitrates, phosphates, etc., will have some vibrations in the mid-infrared region. And here, for example, is the spectrum, the typical spectrum for the carbonate anion, which is with this very broad band in around the 1500 inverse centimeters. So how to identify molecules using infrared spectroscopy? A bit summary. Look at the high wave number end of the spectrum, above 1400, around above 1500 inverse centimeters. Focus on the major bands. Try to find a band that could be indicative of a carbonyl group, or a hydroxyl group, or a nitrile carbon nitrogen triple bond. You might want to have a look at the region around 3000 where the carbon hydrogen stretching bonds appear, and you might be able to identify whether you have an alkene, alkane, or alkyne in your structure. Use positive and negative evidence. The absence of a band is as important as the presence. So the absence of a band in the 1700 inverse centimeters region, a strong band, means that compound is unlikely to be a carbonyl compound. The absence of a very broad band in the region of 3500 inverse centimeters, that would mean that it's unlikely that compound is going to have a hydroxyl group, it's going to be an alcohol. So focus on the presence of bands, but also the absence of bands typically associated with functional groups. A very simplified table, a very simple table of some key bands that is always worth searching to see if you have them, because they are very clearly they can provide a very clear indication that those particular functional groups are present. So the hydroxyl group, the amino band can also, the stretching vibration can also be useful. The nitrile group, the presence of a carbonyl group, etc., can be sometimes quickly identified just by looking at the spectrum and seeing the presence or absence of those bands. This is one possible table of infrared, containing typical infrared bands. In this case, for oxygen-containing compounds. I've provided you with links to other tables on Blackboard. They can be very useful sometimes. For example, to identify, here you have some examples of where an aldehyde appears, where a ketone appears, where an ester appears, where a carboxylic acid appears, and as you can see, there are some difference in the position of the carbonyl group in all those different types of compounds that have all a carbonyl group in their structure. However, it can be sometimes difficult to, the regions overlap, so this is only indicative. Is the presence of additional bands that you might be able to spot, like for example a broad band corresponding to hydroxyl group combined with a carbonyl group is likely to indicate the presence of a carboxylic acid. Rather than being too strict about where exactly that carbonyl group appears. These are just typical ranges. They do not reflect exactly all the possible combinations. So use these tables as indicative of the position rather than a fix. It can only be between these two wave numbers. Otherwise, it's not a carbonyl of an aldehyde group. This is not the way to use the tables. Keep an open mind and keep flexible. That is around 1700, around 1800 in your identifications. So a little bit about the strengths and weaknesses of infrared spectroscopy. Well, it's a great technique. You can analyze solid liquids and gases, semi-solid, powders, polymers. You can analyze almost anything using infrared spectroscopy. It gives you information about functional groups. So you can identify the various functional groups in an organic compound. Is less useful in inorganic compounds because there are fewer that appear. But for organic chemistry, it's really useful. You can use the fingerprint region, not yourself, but if the compound has already been analyzed and you have access to a database, you can identify the compound by using the fingerprint region because it's specific to that compound, and no other compound will have a fingerprint region. The only difficulty or limitation is that it cannot identify between two enantiomers because they have the same structure, so the vibrations will be identical. It's fast and easy to use, it's very sensitive, and it's relatively inexpensive. An infrared spectrometer, it will set you back a few £1,000 rather than £100,000 that gas chromatographer mass spectrometer, for example, can cost. As with anything, it has some limitations. It cannot handle mixtures. If you do the infrared spectrum of a mixture of compounds, you will get a mixture of those spectra for all those compounds. So that can be very difficult to analyze. You will really not know what you're having. You cannot know if that carbonyl group or that hydroxyl group correspond to the same compound, or if you have a mixture with a hydroxyl group and a carbonyl group. One compound has a hydroxyl group and one a carbonyl group, and you run the spectrum of the mixture, you will see a combination of all those groups in the same spectrum. Mixture in aqueous solutions are difficult to analyze just because the broadness of the hydroxyl band can really deform the spectrum. It's very wide and it occupies half of the spectrum, and the other half, the peaks, the bands tend to be very small. Doesn't give you molecular mass information. You know that you don't know the molecular mass, the composition of that compound, and as I mentioned before, it does not distinguish optical isomers. If you have two enantiomers, they will have the same infrared spectrum. So this is all from me. I hope it was useful. Please, if you have any questions, contact me. My email is everywhere on Blackboard, and you have it in this slide. And I hope you have enjoyed the videos and they have been useful. So thank you very much for watching.